What specific problem does the proposed method aim to address in the context of superalignment and weak-to-strong learning?
The proposed method aims to address the challenge of superalignment, specifically the ability of humans to effectively supervise and align the behaviors of significantly stronger AI models with human values. It does this by exploring the weak-to-strong learning paradigm, where a weak teacher model, like GPT-2, is fine-tuned on task-specific data to generate labels for training a stronger student model, like GPT-4. The method investigates whether the student model can outperform the teacher model despite the imperfections in the teacher's labels, thereby demonstrating the weak-to-strong generalization phenomenon. This is crucial because it suggests that even with a less capable teacher, a stronger student can still learn effectively, which is essential for ensuring that future AI systems align with human values. The research also emphasizes the importance of early stopping during training to prevent overfitting to the teacher's errors, thereby enhancing the potential for successful weak-to-strong generalization.
How does the proposed weak-to-strong learning method work? Illustrate the methodology step by step, particularly focusing on the training process of both the teacher and the student models.
The weak-to-strong learning method involves a systematic training process where a weak teacher model supervises a stronger student model. First, a weak teacher model, such as GPT-2, is fine-tuned on task-specific data with true labels to simulate a human who has some mastery of the task. Next, this teacher model generates labels for a dataset, which are then used to train a significantly stronger student model, like GPT-4. The training of the student model is conducted using gradient descent with a critical component of early stopping, which prevents overfitting to the teacher's errors. This methodology allows the student model to leverage its superior capacity to understand the essence of the task, leading to improved performance even when trained on imperfect labels generated by the teacher.
Can you provide a simple yet illustrative example demonstrating the inner workings of the proposed algorithm, specifically the transition from the teacher model's imperfect labels to the student's training?
In the proposed weak-to-strong learning setup, consider a scenario where a weak teacher model, such as a 2-layer network with 8 hidden units, is trained on a specific task using true labels. This teacher model generates imperfect labels for a dataset, which are then used to train a stronger student model, like a 2-layer network with 27 hidden units. The student model, despite receiving these imperfect labels, can leverage its greater capacity to understand the essence of the task, leading to improved performance. A crucial aspect of this process is the implementation of early stopping during training, which prevents the student from overfitting to the teacher's errors. By stopping training at the right time, the student can effectively learn from the teacher's outputs, resulting in a significant reduction in its error compared to the teacher's, demonstrating the weak-to-strong generalization phenomenon.
What are the theoretical and practical benefits of using this weak-to-strong learning method over traditional methods, particularly regarding efficiency and accuracy?
The weak-to-strong learning method offers significant theoretical and practical benefits over traditional methods, particularly in terms of efficiency and accuracy. Theoretically, it demonstrates that a stronger student model can achieve significantly lower error rates than a weaker teacher model, even when the teacher's labels are imperfect, as shown by the weak-to-strong generalization phenomenon. Practically, this method allows for the effective training of advanced models like GPT-4 using a less capable teacher model, which can lead to improved performance without requiring extensive labeled data. The use of early stopping during training is crucial, as it prevents overfitting to the teacher's errors, thereby enhancing the student's ability to generalize from noisy labels. Overall, this approach not only improves accuracy, but also increases training efficiency by leveraging the strengths of a strong model while mitigating the limitations of a weaker one.
How is the method validated or tested? Discuss the experimental design benchmarks used, and how performance is measured to demonstrate the effectiveness of the weak-to-strong generalization phenomenon.
The method is validated through a series of experiments that involve training 2-layer networks with random features, specifically using ReLU and linear activation functions. The experimental design includes a weak teacher model, which is fine-tuned on task-specific data with true labels, and a strong student model that is trained on labels generated by the teacher. Performance is measured by comparing the population losses of the teacher and student models, denoted as L_T and L_S, respectively. The results demonstrate that the student model can achieve significantly lower error rates than the teacher, with the performance gap being quantified through metrics such as the performance gap recovered, PGR, which can approach 1. Additionally, experiments show that the student loss decreases polynomially faster than the teacher loss, confirming the weak to strong generalization phenomenon. The findings are supported by simulations that illustrate the relationship between the sizes of the networks and their respective performance, particularly highlighting the importance of early stopping in achieving optimal results.
What specific results were achieved with this method in terms of error rates for both the teacher and student models? How do these results support the claims made about weak to strong generalization?
The paper demonstrates that weak to strong generalization can lead to significant improvements in error rates for student models compared to teacher models. Specifically, it establishes that the student model can achieve an error rate that is polynomially smaller than that of the teacher model, with an exponent greater than 17, indicating a substantial performance gap. For two-layer ReLU networks, the student model's error can be arbitrarily smaller than the teacher's, with the performance gap recovered, PGR, approaching 1. In the case of linear networks, the student error is shown to be quadratically smaller than the teacher error, confirming that the student can effectively learn from the teacher's imperfect labels. These results collectively support the claims of weak to strong generalization by illustrating that even with a well-trained teacher, the student can significantly outperform it, thereby validating the potential for effective learning in this framework.